So, welcome to our fifth lecture, dealing with gas laws. Now that we have PV equals nRT, the ideal gas law, we can start using it to solve problems with gases. How many moles of helium are needed to fill a 10-liter gas cylinder to a pressure of 65 atmospheres at 25 degrees? If you go into a Dollar Tree or something, they blow up helium balloons for you from inside your gas cylinder. So how many moles of helium would actually be in that gas cylinder? Well, we can use our gas law, PV equals nRT. We have three of our variables, the volume, the pressure, and the temperature, and so we can solve for the last one, the amount of gas. But we're going to have to use an R. And of course, when we talked about R, as we said, you have to be careful which R you are going to use in your problem, because the values of R depend on what units you are using to make all your measurements in. If your measurements are in liters and atmospheres and moles in K, then you have to use the 0.08206. If they are in liters and torrs and moles in K, you have to use 62.36. And if they're in liters, kilopascals, moles, and K, you have to use 8.314 for your R. In our case, we have liters, atmospheres, and Celsius. But of course, in any gas law problem, you have to use absolute temperatures. And so we're going to have to change the Celsius to Kelvin. So our temperature is 298 Kelvin. And so we have liters, atmospheres, Kelvin. We're solving for moles, so we have to use the 0.08206 liter atmospheres mole K version of R. We rearrange our PV equals nRT to solve for N, and we get the answer of 26.58064,896, or in other words, 26.6 moles of gas are needed to fill the cylinder. Let's do another one. What is the pressure in atmospheres inside a 20-liter balloon, which contains 0.5 moles of methane at 20 degrees Celsius? Well, again, we start out PV equals nRT, divide both sides by V, and we get the pressure is equal to nRT divided by V. We got 0.05 moles. Again, it asks for atmospheres, liters, moles, and of course we have to use Kelvin, so it's again going to be the 0.08206 as our R. The temperature 293 Kelvin because we have to use absolute temperature. The volume is 12 liters, and we get pressure is equal to 0.1001815,833. Moles cancel moles, liters cancel liters, K cancels K, and we're left with a pressure. The pressure should be 1 atmosphere. So what volume is occupied by 21 grams of nitrogen at 25 degrees Celsius with a pressure of 97.6 kilopascals? So again, we have an amount of gas, we have a temperature and a pressure, so we can use our gas law to solve for the fourth variable, the volume. PV equals nRT divided by P. Volume is equal to nRT divided by P. In this case, we have kilopascals and Kelvin. So we're going to have to use the 8.314 kilopascal liter mole K version of R. The temperature, of course, has to be 298 Kelvin. It has to be the absolute temperature. The pressure, 97.6 kPa. And finally, need the amount of gas. Well, we can't use 21 grams. Grams is a mass. It's not an amount of gas. And so you're going to have to change the 21 grams of nitrogen to moles. So go ahead and calculate how many moles of nitrogen 21 grams is, and put it in the equation and solve for the volume. You can pause the video while you're doing that. And the answer you get is 19 liters. What, you didn't get 19 liters? Well, maybe you made a fairly simple mistake. We said you have to use N in our equation to solve for the volume, but what does N represent? Well, it represents moles of gas, but not moles of compound or moles of element. It represents moles of particles. How many separate particles do you have? We said the gas laws don't care about what the gas is, but it does care how many separate independent things you have wandering around. And nitrogen all by itself is, of course, in the form of molecules. Along with who else? That's right. Hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, and iodine are the 6 gases you have to pay attention to because they are molecules in the gas phase. So the 21 grams of nitrogen is divided by 28.02, the molecular weight of nitrogen, to give us 0.7495 moles of nitrogen times our 8.314 R times 298 Kelvin divided by 97.6 kilopascals. We get 19.02512986. Moles cancel moles, kilopascals cancel kilopascals, K cancels K, and we're left in liters, and so the answer is 19.0 liters. Okay, and what temperature would 1.5 moles of carbon dioxide fill a 40-liter balloon with a pressure of 755 torr? Again, PV equals nRT. This time we're having to solve for T. So PV divided by nR, 7.55 torr, 40 liters, 1.5 moles. And in this case, the R has to be the one that includes torr. So 62.36 torr liter moles Kelvin. Do the calculation, 372.8565 Kelvin, which is 373 Kelvin, which is 50 degrees Celsius. Let's try something a little more complicated. What is the pressure in atmospheres inside a 20-liter gas cylinder that contains 10 grams of neon and 15 grams of argon gas at 25 degrees? Well, we said we can't use mass. We have volume and temperature, but we're going to need moles, so we're going to have to change the neon and the argon to moles. Well, 10 grams of neon, the atomic weight of neon, 20.18, so that's 0.4955 moles of neon. PV equals nRT, so 0.495 moles times 0.08206 liter atmospheres moles K times 298 Kelvin, got to always use Kelvin, divided by 20 liters. And so we find out the pressure exerted by the neon. We talk about the partial pressure of neon inside the gas cylinder is 0.6058 atmospheres. But that's only the neon. Now we have to do the argon. We have 15 grams of argon. The atomic weight for argon, 39.95 grams per mole, gives us 0.3755 moles of argon. Put it in our equation, and we find out that the partial pressure of argon, 4.591 in atmospheres. And so now we could solve for the total pressure straightforwardly. The N is the number of moles of gas. Well, that'd be the 0.3755 moles of neon plus the 0.4955 moles of argon. Do the rest of the multiplication, and that would give us the pressure of the total gas, or we can use what is known as Dalton's law. After all, the neon is exerting 0.6 atmospheres of pressure. And it doesn't care whether the argon's there or not. It's pushing on the walls with 0.6 atmospheres. In the same way, the argon is pushing on the walls with 0.45 atmospheres of pressure. And it doesn't care if the neon's there or not. It's doing what it's doing. And so the walls are feeling the sum of those two pressures. The 0.60 atmospheres for the neon and the 0.45 atmospheres for the argon, and so the wall is feeling 1.065 atmospheres of pressure. And this is known as Dalton's law of partial pressures. The total pressure of a gas of a mixture of gases is simply the sum of the partial pressures of each of the gases. So now we've used our gas law to solve for all of our variables: temperature and volume, pressure, and the amount of gas. So what else can we do with the gas laws? So how many grams of water can be produced by burning 1 liter of methane at 25 degrees and 95.4 kilopascals pressure? Methane is the main ingredient in natural gas. So when you are cooking something on a natural gas stove, what you are burning is methane. So how much of this do you get if you use that? It's stoichiometry. So 1 mole of methane reacts with 2 moles of oxygen. You get 1 mole of carbon dioxide and 2 moles of water. The next step is go to moles. Well, we don't have mass and we don't have solution. What we have is a gas, but we have a volume, a temperature, and a pressure, and that permits us to solve for the fourth of our variables. PV equals nRT. N is therefore equal to PV divided by RT. 95.4 kilopascals, 1 liter, 298 Kelvin. We're going to have to use an R that includes kilopascals, so it's 8.314 kilopascal liter mole K. 0.03851 moles of methane are produced. 1 mole of methane produces 2 moles of water. A mole of water weighs 18.02 grams per mole. So we can produce 1.39 grams of water by burning 1 liter of methane at 25 degrees and a pressure of 95.4 kilopascals. And so we can use our gas laws to solve stoichiometry problems. They provide a number of moles. And in the last step, that means we can have the answers to stoichiometry questions that include other things besides grams. We can now have volumes and pressures as answers as well. How many liters of CO2 can be produced at 25 degrees and 0.983 atmospheres of pressure by reacting 10 grams of sodium carbonate with HCl? Again, how much of this do you get if you use that? It's stoichiometry. The first step is balance the equation. 1 mole of sodium carbonate reacts with 2 moles of HCl. You get 2 moles of sodium chloride, 1 mole of water, and 1 mole of carbon dioxide, which is going to come off as a gas. So it's going to be in the gas phase. 10 grams sodium carbonate divided by 105.99 grams. That's the formula weight for sodium carbonate. 1 mole of sodium carbonate produces 1 mole of CO2, so we're going to produce 0.09435 moles of CO2. PV equals nRT divided by P, the volume that 0.09 moles of gas will occupy, times 0.08206 liter atmospheres moles K, times 298 Kelvin divided by 0.983 atmospheres of pressure, 2.347, etc. So 2.35, moles cancel moles, atmospheres cancel atmospheres, Kelvin cancels Kelvin. So we could produce 2.35 liters of CO2 from this reaction. And so the gas laws provide us with another way of doing stoichiometry. We've done it with solids using mass, we've done it with liquids using volumes and molarity, and now we can use it for gases using pressure and temperature and R to get our answers in the moles and volumes. And that brings us to the end of the chapter on gas laws. Start the next chapter next week.